An ideal gas at 17 degrees Celsius has a pressure of 760 millimeters of mercury and is compressed isothermally and later adiabatically until its volume is half, in each case reversibly. Calculate in each case the final pressure and temperature of the gas, assuming Cp, that is molar heat capacity at constant pressure, equals 2.1 kilojoules per kilogram per Kelvin, and Cv, molar heat capacity at constant volume, equals to 1.5 kilojoules per kilogram per Kelvin. So for us to solve this now, all I need to bring forward here is, you must remember that this is an isothermal expansion. For an isothermal expansion, for an isothermal change or expansion, you have PV equals to constant. So that means an isothermal change follows Boyle's law, because in an isothermal change temperature is constant. So how do I need to do here? Just generalize this formula. It becomes statement of Boyle's law, P1 V1 equals to P2 V2. Now go back to the question. An ideal gas at 17 degrees Celsius. We don't need the 17 degrees Celsius for the isothermal process, because in an isothermal process or change, temperature is constant, so the temperature will not change for an isothermal process. So all I need here is look at the pressure. The P1 is given as P1, the initial pressure, 760 millimeters of mercury. Now what will be the V1? Look at the question. Adiabatically until its volume is half, in each case reversibly. That is, V1 is a certain volume, which is V, a certain volume, certain volume unknown. Then V2 until its volume is half, in each case. That is, V2 is half of V1, half of the initial volume, which is same thing as half of V, since V1 is V. So we have the statement of Boyle's law settled. What is left now is to look for the P2. So if I want to get the P2, which is the final pressure, because the question says calculate final pressure and temperature, so bring this formula back, that okay, P1 V1 equals to P2 V2. P1 is 760 times V1 is V, P2 is unknown, then V2 is half of V. So here now you have 760 V equals to P2 times 1 times V, that is P2 V, everything over 2, which is this half. So from here now I can have it that this V cancel this V if you cross multiply. So if you cross multiply now, you can have this is over 1, cross multiply, P2 will be 760 times 2, and if we do that, 760 multiplied by 2, that gives 1520. That means the final pressure is 1520 millimeters of mercury. So we have been able to get the final pressure for the isothermal process. So again, for an isothermal expansion, note the final temperature is still 17 degrees Celsius. Why? In an isothermal process, temperature is constant. That means temperature do not change. For constant temperature in an isothermal process or change. Now what have you observed? That first part, for isothermally, we've answered the pressure. This represents pressure. This is the final pressure, and the final temperature also is still 17 degrees Celsius. So we are through with isothermal. Then we can proceed to the next one, which is Again, adiabatically, you are asked to look for, again, it's adiabatically look for the final pressure and final temperature adiabatically until its volume is half in each case, also reversibly. Calculate in each case the final pressure and the final temperature of the gas, assuming that Cp, now we have been given the Cp to be 2.1 and Cv to be 1.5. So you know that for the adiabatic change B now, adiabatically. Now for adiabatic, you have PV gamma equals to constant. That's how we get the pressure. We've derived this equation in the previous video. So what are we making use of here? This gamma is the ratio of the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. That means Cp, which is given as 2.1, you have to divide it by Cv, which is given as 1.5. So if we do that, that will give you 1.4. That means gamma is 1.4. So you generalize this equation. If you generalize this equation now, generalizing this equation, that means you are going to have P1 V1 gamma equals to P2 V2 gamma. So how do we go with this again? P1 is 760 millimeters of mercury. It doesn't change, but you cannot say P2 is 1520. This is the final pressure for the isothermal change, not for the adiabatic. So P1 is 760 times V1 is V, which is gamma raised to power 1.4. The ratio of molar heat capacity equals to P2 unknown times V2 is half of V, which is V over 2, with ratio of gamma 1.4. So here now I have 760 times V raised to power 1.4 equals to P2 times, if you open this bracket, you have V raised to power 1.4 over 2 raised to power 1.4. You see that? We just open the bracket, then you can have 760, or we can just say 1.4 cancel 1.4 here. V of 1.4 on this side, cancel the V of 1.4 on this side. So you are left with 760 760 equals to P2 over 2 raised to the power of 1.4. So if you cross multiply, let's go to the next page. You cross multiply now. Last was 760 equals to P2 over 2 raised to the power 1.4. This will now be over 1. If you cross multiply, P2 will be 760 times 2 raised to the power 1.4. So let's multiply that. 2 raised to the power of 1.4 times 760, that gives 2005.6. So you can approximate it as 2006. Pressure is in millimeters of mercury. Now this is the pressure when the gas expands adiabatically, the final pressure also. So this is the final pressure P2. So once you have the final pressure also, you also need the final temperature. The final temperature. So how do we get the final temperature? Now for the final temperature, you bring in the equation. Now final temperature will be, for an adiabatic change, you go with T V 1 gamma minus 1 equals to constant. Now this is a statement of Charles' law, volume and temperature. Okay, so at this point you generalize this left hand side. If you generalize that, it's going to be T1 V1 gamma minus 1, which is equals to T2 V2 gamma minus 1. So what do I need to note here? Note T1 is given in this question, which is at 17 degrees Celsius, and you have to convert that 17 degrees Celsius to standard temperature in Kelvin. So that will be what? To Kelvin now it will be 17 plus 273, and that will give us 290. So you have the 290 Kelvin. You have converted that. The initial volume V1 is V. V1 is V. So V1 is still V, and gamma is 1.4, and T2 is what we are asked to look for. So therefore we'll go with T1. T1 now is 290 times V1, which is V, gamma is 1.4 minus 1, equals to T2 unknown, which is what we are asked to look for, times V2. V2 is V divided by 2 with gamma. Gamma is 1.4 minus 1. So here now you have 290 times V. 1.4 minus 1 will give 0.4, equals to T2, close the bracket here, times V2. 1.4 minus 4, V2, that is 0.4. you are putting the bracket over 2 again, raised to power 0.4. This 0.4 of this cancel this 0.4, so we can have 290 equals to T2 over 2 raised to power 0.4. If you cross multiply now, T2 will now be 290 times 2 raised to power 0.4. so let's multiply that. 2 raised to the power 0.4 times 290, and that will give 382.65, which is approximately 383 in Kelvin. So what if I ask you to give the final temperature in degrees Celsius? So in degrees Celsius it will just be 273 minus that value. So with 383 minus 273, and that will be 110. So this will give 383 in Kelvin, or 110 degrees Celsius. Therefore the final temperature now when the gas is compressed adiabatically is 383 Kelvin, and the final pressure is 2006 millimeters of mercury, while that of the isothermal process final temperature remains 17 degrees Celsius or 293 Kelvin and 290 Kelvin, and the final pressure remains 1520 millimeters of mercury. So let's proceed to the next question. Now the next question here, you have what we have here is a gas cylinder is kept at a temperature of 30 degrees Celsius and a pressure of 10 millimeters of 10 raised to power 5 Newton per meter squared, is compressed to 1/8 of its volume adiabatically. Now what we observe here is still an adiabatic process. Determine the final pressure and temperature, and you are given that the ratio of the molar heat capacity is also 1.4. So all I need here firstly is to bring out the statement that okay, this is adiabatic, then we are working with PV gamma equals to constant, in which I will generalize this, which will become P1 V1 gamma equals to P2 V2 and with gamma. So in this case P1 is going to be the first pressure that was given in the question, 10 raised to power 5 Newton per meter squared, and V1 is a certain volume, which is V, and V2 again becomes compressed to 1/8 of its volume. So V2 is 1/8 of V1, which you can write as V1 is V, so V over, instead of that, 8. So V2 is V over 8. Then we are asked to look for what? The final pressure. The final pressure will be P2, which is unknown. So how do we get the final pressure here now? Put all this value into this P1 now, and the ratio of molar capacity is 1.4. So anywhere we see gamma 1.4. So P1 we have 10 raised to power 5 times V1, which is V raised to power gamma 1.4, equals to P2. P2 is unknown, times V2 is V over 8, all raised to the power of what? Gamma, which is 1.4. So this will be 10 raised to power 5 times V 1.4 equals to P2 times V, then open this bracket, that is 1.4 over 8 raised to the power of 1.4. Now take note, you have 1.4, 1.4, so I can have it that, okay, this V raised to power 1.4 cancel this V raised to power 1.4, then I'm left with 10 raised to power 5 equals to P2 over 8 raised to the power of 1.4. So if you cross multiply, you can have the final pressure P2 to be 10 raised to power 5 times 8 with 1.4. So let's multiply that. If you multiply that, that will give final pressure to be 1.84 times 10 raised to power 6 times 10 raised to power 6 Newton per meter squared. Now we have the final pressure. So what do I need again? We need to calculate the final temperature, and if we are calculating final temperature, you go with a statement of Charles' law. And what is that statement for temperature? In the previous example, you have it as T V gamma minus 1 equals to constant. This is how you calculate temperature of an adiabatic change. So how do we go with this? Generalize this. This becomes T1 V1 gamma minus 1 equals to T2 V2 gamma minus 1. So T1 is the initial temperature. The initial temperature in this case is 30 degrees. So if you have 30 degrees, the cylinder is kept at 30 degrees. I need to convert this to Kelvin, which will now be 30 plus 273, and that will give you 303 Kelvin. So we have the initial temperature now. So anyway, I see T1 303, T2 is unknown, which is what I'm looking for. V2 is V over 8, and gamma is 1.4. 1.4 minus 1, which will lead us back to 0.4. So this will now give 303 times V1 V 1.4 minus 1 equals to T2, then V times, this is now V over 8, 1.4 minus 1. So this will be 303 times V raised to power 0.4 equals to T2 times V, open the bracket, 0.4 over V 8 raised to power 0.4. So 0.4 here, cancel the other 0.4. So you have 0.4, cancelling this 0.4, we are left with 303 equals to T2 over 8 raised to power 0.4. So if you cross multiply, T2 will now be 303 times 8 raised to power 0.4, and that will give us a temperature of 696 in Kelvin. And if you want to put that in degrees Celsius, subtract 273 from that, and that will give 423 degrees Celsius. Confirm that. 696 minus 273, which is 423 degrees Celsius. So the temperature in degrees Celsius, which is the final temperature, is 423 degrees Celsius, while the initial temperature in degrees Celsius is 30 degrees Celsius. Now once you have done that again, we've answered enough question on temperature stuff. So let's proceed again to the next example. The next example is assuming that the ratio of the specific heat capacity of hydrogen is 1.41. Specific heat capacity of hydrogen is 1.41, and that its density at STP is 0.09 kilogram per meter cube. Find a value for specific heat capacity at constant volume in joules per kilogram per Kelvin. Now watch out, in this question now you have STP, standard temperature and pressure, but one thing you must note is you have been given that the ratio of specific heat capacity is 1.4. What does the ratio mean? That means you have been given gamma, which is the ratio of CP over CV. So that means I've been given gamma to be 1.41 equals to CP over what? CV. So from this part I can make CV the subject and CP the subject of formula. If you cross multiply, CP now will be 1.41 CV, right? Okay, call this, keep this, that is 1. Now, and that its density at STP, density has been given as 0.09 kilogram per meter cube. Find the value for specific capacity at constant volume. That means CV is the main question here, but you must recall that R, which is the molar gas constant, CP is CP minus CV. So how do we now do this? You have a value for CP already. CP is 1.4 of CV, so we have that, but we don't have a value for R. So how do I get R? You go back to the equation of an ideal gas equation. From an ideal gas equation, what do you have there? You have PV equals to what? RT. So all I need to do here is to make my R the subject of formula, so that once we have the value for R, we fix in the value here and we can have the value for that CV. So that means here now, make R the subject of formula. R will be PV over T. Now, but what we have here, we are not given pressure directly in this question, but instead of that we are given density and then so on. So how do we express density? Keep this as equation 1. Density, which is rho, is what? Mass over volume. So how do I now make volume the subject of formula? If you make volume the subject of formula here, from here volume becomes mass over density. So anywhere I see volume in this equation now, I'll turn it to what? Mass over density. So if you do that, you have R equals to P, volume is mass divided by density, everything over T. So let's go to the next page. So if you simplify that correctly, the last part, R equals to P, which is the pressure, you have mass over density, then everything to be divided by what? Temperature, then over 1. So R here now gives pressure, which is P M over density times 1 over temperature. So that means the real expression will be R will be pressure mass over density multiplied by temperature. Now you are good to go. At STP, the standard temperature at STP is going to be 273, and the standard pressure at STP, standard temperature and pressure, standard temperature, which is your T, is going to be 0 degrees Celsius, which is 273 Kelvin, and the standard pressure, which is P in this question, will be 1.013 times 10 raised power 5 in Newton per meter squared. Why? Because that is what we are asked to go with. because we are working with pressure in Newton per meter square. Why? Because we have density given in that same value. So all I need to do now is to put in these two values back to this part. So if I do that, you are going to have what? R here equals to pressure 1.013 times 10 raised to power 5 times the mass is per kg, which is 1, over the temperature 2, the density 0.09 times temperature is 273. So if you multiply that R and you divide, you are going to have 4.12 approximately. Let's multiply 1.013 raised to power 5, okay, 0.09 times 273 equals to this 0.09 times 273 this. So 1.013 raised to power 5 divided by answer here, that will be 4. That will give R to be 4122.9, and that is in joules per kilogram per Kelvin. But I need this in kilojoule, it's too big. So in kilojoule, how do I get it in kilojoule? Divide what you have there by 1000. So that will make R to be 4.approximately 12 kilojoules per kilogram per Kelvin. Now that we have a value for R, all I need to go back to do now is to record that. My R is what? Cp minus Cv, and from the beginning we have Cp to be equals to 1.41 Cv. So anyway I see R here, I replace it with 4.12, so I have 4.12 equals to, anywhere you see Cp, 1.41 Cv, then minus Cv. It's like you are saying 1 minus 1 Cv. So if you subtract that, you have 4.12 equals to 1.41 minus 1, that will give you 0.41 Cv. So that means Cv, which is what you also calculate, to be 4.12 divided by 0.41. Let's divide that. 4.12 divided by 0.41. That will make the value to be Cv. Cv is now 10.0 approximately 5, which should be in, what is the unit for the Cp that was given? In joules, kilojoules per kilogram per Kelvin. And you have answered that question, which is calculate the molar heat capacity at constant volume. So the molar heat capacity at constant volume, Cv, molar heat capacity at constant volume, is this. So let's proceed again. Lastly, now you have a question here that the two principal molar heat capacity of oxygen, calculate the two principal molar heat capacity of oxygen if the ratio, now ratio has been given, so just come and notify that quickly, note it down. Ratio gamma is 1.40. good. Then you have density of oxygen, density, so this is similar to the previous example, at STP 1.43 kilogram meter per meter cube. Now one standard atmosphere, so pressure has been given, which is 1 times 10 raised to power 5, and molar mass of oxygen. Now molar mass is capital M. Molar mass, capital M, for oxygen is 32 times 10 raised to power minus 3 kilogram per mole. So what do I need here? I'm asked to calculate the two principal molar heat capacity. What are the two principal molar heat capacity? That is Cp1 at the same time Cv. So all we have to do now is to recall the formula that for an ideal gas, next page, let's make it black. Good. So I'll just record that for an ideal gas, for an ideal gas, you have it that what PV equals to RT. So I can make R the subject of formula so that we can have an expression for R. R will now be PV over T. Now that you have PV over T, put in the value P. Lastly, we got P as, which was given 1 times 10 raised power 5. Then the volume is 1 per volume, and the temperature is at STP 273. At STP 273. But now molar mass is given in this question, so going with this will really mean another challenge for us to solve this question. So how will I go now? Just still maintain this ideal gas equation. Let's go with PV equals to NR with T, since molar mass is given. So you have to look at this N. N here means number of moles. And what is number of moles? Definition: number of mole is what? Reacting mass over molar mass. So reacting mass is M and molar mass is capital M. So this has been given, molar mass has been given. So how do we do that? Go back to that equation, which is PV equals to nRT. So you have PV, anywhere we see N, it becomes M over molar mass with what? RT. So if we cross multiply, we are going to have PV M, capital M, equals to small m with RT. So I need a value for the molar gas constant R. So R, if you make R the subject of formula, R will be PV molar mass over MRT. So what is the pressure? Pressure in that question is 1 times 10 raised power 5, which is this. Now I'm back to this. Pressure is, so let's manage this. R equals to PV molar mass over mass and temperature. So the pressure is 1 times 10 raised power 5, and the volume of this gas, the volume of the gas is volume of this gas. Look at it here. We have an expression for that, but the molar mass here is 32 times 10 raised to power minus 3 over, we have not substituted value for V and M, but you must record that what? Density is what? Mass over volume. So 1 over density becomes volume over mass. So this volume over mass here is simply 1 over density. So you can have this formula to be P molar mass, instead of volume over density, it will now be density times temperature. So all I need to substitute now is density. Density in the question is 1.43, the density. So you have 1.43, then times the temperature at STP, which is, we are back to this now, standard temperature 273. So R gives, if you multiply that, you are going to have your R to be 8.197 in kilojoules per kilogram per Kelvin. Now that you have this, what are we asked to look for? The ratio of the two molar heat capacity, that is R, which is Cp minus Cv. So how do we get that? Go to the introduction of this question. We have an expression for that. Back. Good. gamma is 1.40, gamma is 1.40, which is ratio of molar capacity. So if gamma is 1.4 and gamma is always Cp over Cv, that is 1.4 equals to Cp over Cv. So make Cp the subject of formula. Cp becomes 1.4 Cv. So anywhere we see Cp here, I'll replace it with 1.4 Cv. Now that will give us a value for Cv, and R is available. So put that. You will now have, let me pick another color of pen. So this will give R is Cp minus Cv. So R is 8.197 and Cp is 1.4 Cv minus Cv, which is 1 Cv. So let's proceed to the next page. Change it. Good. So that last part is 8.197 equals to 1.4 Cv minus Cv. So if you subtract that, you are going to have here 8.197 and 1.4 minus 1, 0.4 Cv. That means Cv will be 8.197 over 0.4. So 8.197 divided by 0.4, 8.197 divided by 0.4, that will give 20, which is 20.49, and that will be kilojoules per kilogram per Kelvin. Now you have gotten a value for that. Then how do we now get a value for Cp? Remember that Cp is 1.4 of Cv. So all I need to do is Cp will be 1.4 times, what is Cv? The last value, 20.49. So multiply it by 1.4, and that gives Cp to be 28.69, which is in kilojoules per kilogram per Kelvin. Now how do I know maybe what I've done is right? If I want to just confirm it, I can just go back, okay, by saying note. Maybe I just want to check. Let's try it out. I can say gamma is what? Cp over Cv. Let's try to divide these two values. Maybe it will give us 1.4, which was given as gamma. So you are going to have 28.69 divided by 20.49. So 28.69 divided by 20.49, and that gives exactly 1.40. So that shows that what we have done so far is also right. So all I need here is settle down with these examples, try some questions. If you have any other questions, feel free to send them, and make sure you study hard, including your past question.